Next up, we have ZFS in space with Phaedrus Leeds.
Hello. Is the mic still working? Is it good? Okay. So yeah, my name is Phaedrus Leeds. I'm on the small satellite team at the Aerospace Corporation in X Lab, which is the prototyping department. And my department has about 2 decades of history running CubeSats, and even before the CubeSat standard existed. So for this talk, I'm going to start by talking about the EdgeNode and EdgeNode Lite missions, which are upcoming CubeSat missions. Then talk about the hardware and software architectures for those missions. Go over some information about radiation in the space environment and mitigation strategies. Talk about qualification of the EdgeNode hardware for space radiation. And then finally, ZFS, which is kind of the main topic at the software layer as a layer of protection for space radiation. So first, EdgeNode is a multi-vehicle rendezvous and proximity operations testbed for advancing autonomy algorithms. It's going to be 6U CubeSats that are going to have a number of different sensors on them. You can see millimeter wave, infrared, visible light, LiDAR, etc. And they're going to support running experimental algorithm payloads from, external partners or whoever wants to advance their algorithms for autonomy in space. We're also interested in doing things like sensor fusion, taking all of this data from these different sensors and combining them to try to understand the environment. A lot of interesting applications there. This is another slide with more information on it. I'd like to point out the NVIDIA TX2 SOMs, since that's kind of the main focus of this talk. Those are providing almost all of the, large horsepower compute available for processing the sensor data and running experiments. That's NVIDIA hardware that has, a GPU, CPU, and memory all on one chip and has, it's relatively powerful, running Linux. There's also steam propulsion and laser downlink and a couple different forms of crosslink. So for our software architecture, it's going to utilize SatCat5, which is an open source project from Aerospace that provides an Ethernet switch, as well as a number of other different interfaces to hardware like UARTs, for example. And we're going to use, as I mentioned, Linux running on that NVIDIA SOM. In the case of EdgeNode, there's actually going to be 2 different NVIDIA modules running. And that's going to provide, a lot of the software computing. Another thing to point out here is that there's a microcontroller running on each board. So that provides, something that can control the other components and, for example, power cycle them if necessary, or provide more like flight critical functions that we might not want to trust on the same processor that's running the experimental algorithms. So we're utilizing ROS2, which is stands for Robot Operating System 2, as a software layer for interprocess communication and as the layer that is processing the sensor data, essentially. So it's running in between Docker and the applications, kind of as a layer of libraries on the Linux side of things on the Jetson, and then over on the microcontroller, we also have ROS running, utilizing a project called MicroROS, which allows you to put ROS on a microcontroller, but it's only possible by having another process running on your another computer, in this case the Linux one, that does the communication with the rest of the ROS network and is like a middleman between the microcontroller and the rest of the ROS network, because otherwise the constraints of your microcontroller would be too much for ROS to be able to actually run. So here's some of the EdgeNode Lite hardware. That's the mission that's going to launch just early next year as one payload on a CubeSat that also has other payloads. You can see the actual hardware in the below image, and that hardware is just going to have one sensor for that mission, which is an infrared camera. and it's going to provide some like risk reduction of the hardware design before the full edge node mission that's later on, as well as, you know, building out our software design and our processes for, you know, running this mission. So I'm excited for that mission. So now space radiation. I think probably everyone here is aware of it to some extent, but there's some images here you can see of how it changes paint color and damages hardware. And of course, the more intense the environment, the more radiation hardened materials you need. Some systems can tolerate radiation more than others. And radiation generally comes from the Van Allen radiation belts, at least when you're talking about low Earth orbit or similar orbits. And like for those who don't know, in low Earth orbit, the radiation environment is fairly benign, except for the South Atlantic anomaly where radiation is more intense. So a lot of times if you see radiation effects on your computers in low Earth orbit, often it's over the South Atlantic. So single event effects are something that's caused in hardware by a ionizing radiation. They could be direct ionization or indirect ionization. So in other words, ionizing materials through affecting their protons, or ionizing materials through affecting the nucleus that then causes other particles to come out. So there are destructive single event effects and non-destructive single event effects. A non-destructive one, basically you can power cycle it and recover from it, and a destructive one, you can't. For this talk, we're going to be mostly interested in like memory having bit flips as a non-destructive single event effect, and also just other types of hardware failures that require a power cycle even if they're not a bit flip. So some of the things you can do about radiation is to have redundancy. That way, if one device fails, other devices can hold the data. Or, for example, one way of doing this is to have a voting system where you have 3 copies of hardware and then just have them vote. And if one copy fails, the other 2 will still have the correct answer, and you'll notice that and use that. However, there are a lot of considerations still that doesn't actually fix the error. And error correction codes are like another hardware mitigation. But like there are some things to note about that, like you can have a single radiation event cause multiple bits to flip in one word, and then your error correction code doesn't help with that. Or you could just have multiple radiation events over time where they happen too quickly for your error correction code to scrub them away. So for the Edge Node Light mission, we're going to be utilizing NVMe drives, and we wanted to radiation test them to see if they were, which brand would be the best one to use. And we're also using a microcontroller, the SAM-B71, that has a radiation-tolerant version of it. So we took some to a proton beam and tested for single event functional interrupts, which are when you have to power cycle the device to recover. For this particular one, the Western Digital SN530, we saw only less than 1 essentially per year, as if you look at the orbit that we're going to be in. I think about 400 kilometers altitude, whereas some of the other brands suffered 10 times as many. So it was a pretty huge difference between different brands of NVMe drives. So now I'm going to talk about ZFS, one of the options that you have for your file system on Linux. I guess, could I get a quick show of hands of people who've used Linux? Have you ever seen FScheck running when you boot up the computer? Yeah? So that's basically because the default file system for Linux usually is extended 4, and extended 4 does not have consistency guarantees. It's like pretty deep in its architecture is the fact that you can have an operation interrupted by sudden power loss when you, for example, unplug your computer, and the operation wasn't completed, so the file system's in an inconsistent state. Sometimes on the next reboot, you can recover from that state by checking the journal and understanding what operations got done and what didn't. And sometimes you can't recover, and you just hopefully have a backup. For example, the journal could be corrupted, and that's one state where you can't really recover from. So ZFS is an alternative that's been around for quite a while, over 2 decades. And it basically doesn't have that problem. When they were writing ZFS, they tested, power cutoff tons of times, and were able to make sure that it is resilient to that using, a number of different software techniques. And in particular, copy on write is one of the main ones that allows it to have this property of staying consistent all the time, even through sudden power loss. So it's supported on various operating systems. Unfortunately, if you're using Linux, you can't just take an upstream Linux kernel and use it, or except for on Ubuntu, because it's not included upstream. But it does have decades of use on production systems, so it's not something that's like a new piece of software that we have to be unsure about whether it's ready for production. It's highly scalable. It supports data integrity verification and transparent repair, which I'm going to talk about on the next slide. It also has, it's not just a file system, it's kind of also a volume manager. So that allows it to do something like RAID. They call it RAID Z. And it's even better than RAID, because on RAID you can have, if you're writing across multiple disks, you can have your operation get interrupted before you've written the stripe across all the disks, and then you're in an inconsistent state, which is called the RAID 5 write hole. But on ZFS, it doesn't have that problem. I think partly because of copy on write, and partly because it is both a file system and a volume manager, so it's kind of spanning the different layers of the software stack in that way. As I mentioned before, it's highly resilient to sudden power loss, which is great for space systems. And it also has lots of other features that we don't even really have time to get into, like block level deduplication, compression, encryption, smart caching, and more. And I guess I'll also just mention OpenZFS is specifically an open source variant of ZFS, because at some point ZFS kind of went closed source. So yeah, as I mentioned, I guess maybe it's worth mentioning on Extended 4, when you read data from a file, Extended 4 will just give you back the data. And if the hard drive had some problem and the data was corrupted, you don't really know that. You just get corrupt data, and hopefully it doesn't really matter, or hopefully if you really need, your data to have integrity, you're using a checksum in some way. But ZFS is not like that. It will use checksums to ensure that either your data was not corrupted and you get back the same data that you wrote, or your data was corrupted and it can be, another copy of it can be grabbed and used. Or if your data was corrupted and there are no other copies of it, it'll return an error. So at least you know that there was a problem with your data and you're not just using bad data without knowing it, as you might be doing if you're using Extended 4. So more specifically, file metadata, which is like, for example, the information about the directory tree of your file system, is duplicated by default, like even if you're only using one disk. So that means that the file system structure can survive pretty well, even if parts of the hard disk have hardware failures. File content can be duplicated, but there's, of course, a cost to that. If you duplicate all of your file content, that means you can store about half as many files. So you can do that with something called ditto blocks. Even if you only have one disk, you can still have redundancy that way and not lose your file data, even if you have some corruption on parts of the disk. And then if you have more than one disk, you can also do RAID Z, which is providing redundancy across disks. And there's a number of different options for that, like mirroring and or parity blocks that provide different levels of redundancy and have different trade-offs. So yeah, as I mentioned before, ZFS will check your data's integrity when it's being read back, and either repair it if there's another copy available, or return an error if there's not. And in fact, it can even use an in-memory copy. If there are no copies of the data on disk that are not corrupt, but there's a copy in memory that is not corrupt, it can return you that, and then you still have good data. A few other ZFS features that are interesting, snapshots, which are a very lightweight mechanism for rolling back your file system to a previous state. Because of the way that ZFS is architected, with copy on write, you don't need to store much extra data if you just want to preserve a previous state of the file system. It just means that you have that previous state. All those blocks are still being used. So I guess I probably should quickly try to explain copy on write, since it is so important to ZFS. Essentially, the idea is that when you are writing a block of data to the disk on extended 4, if you're writing to an existing block, you would just write to that block your new data that's been modified. And if that operation gets interrupted, then you might have an in-between state where you don't have either the old version of that block or the new version of the block. On ZFS with copy on write, instead of modifying the existing block of data on disk, you just allocate a new block somewhere else, write your new data there, and then do an atomic link operation where your file points to that block as the new one. So you can atomically utilize the new data, and either the power, or if there is a power loss, you have either the new block has been already linked to and you have that data persistent, or if the power loss was right before that operation, you have the old copy of the data, but at least you don't have an in-between state. So ZFS scrubs are a mechanism for checking for the data corruption, even if you're not reading from files, because otherwise, if you don't read from a file for a year, you wouldn't notice that it was corrupt, because usually the integrity verification happens during a block read. So scrubs provide a way to check every single file for corruption, and then you can sleep well at night knowing that your data is all still uncorrupt. Also has a concept of data sets, which is basically just like file systems and other file systems, in that they can be mounted at different places in the file system hierarchy. And they can also have various different properties set on them. So you can turn on or off compression on a certain part of the file system. You can turn on or off deduplication of blocks on a certain part of the file system. You can even set quotas for different parts of the file system. So like you can only have 100 gigabytes of data in your /home partition, and that way your more safety critical perhaps parts of the file system can still continue to function, like your logging perhaps. So yeah, in order to get ZFS running on this hardware that we're going to launch for Edge Light, there was quite a lot of work involved by me, because NVIDIA doesn't really support ZFS. And it was, the hardware platform was utilizing the U-boot bootloader, which in theory has ZFS support, but in practice I found that it didn't actually work. So I had to use some useful printf statements to figure out what was going on and patch U-boot to get the ZFS support working. Those patches were actually just accepted to U-boot a few weeks ago. So if you'd like to look at the actual details of what needed to be changed in U-boot to get ZFS working, you can look at them since they're on GitHub. It was, I guess some of it was mainly around like assumptions of a 32-bit architecture being used, whereas the architecture here is ARM64, so not 32 bits. And then here we just have a graph showing that after going through the early bootloaders, you hit U-boot, and then you can take an action based on one of the GPIO lines, and then load either your regular init RAM disk or a recovery init RAM disk. The init RAM disk is something that loads your final file system from the disk. And in this case, one of our init RAM disks could execute some ZFS commands to restore data from snapshots. So that way we could be confident that if we accidentally overwrite some critical part of the file system, we have a recovery mechanism, a factory reset mechanism that should get us back to a good state. And then as the final step in the boot process, your file system pivots to your final root file system being mounted at / the root of the file system hierarchy. So to summarize a little bit, the two main things that make ZFS useful in space are its resilience to data corruption and sudden power loss, because both of those two things could happen because of space radiation, and they could happen for other reasons as well. Maybe you like run out of power because you have been using your power for something else. And in space systems, you want recovery to be as automatic as possible. On the ground, maybe you can pull out a hard drive and plug in another hard drive, but in space, it's not quite so easy. I believe this mission next year at No Light will be the first use of ZFS in space, which is pretty exciting. And we're going to have some telemetry to monitor, read-write errors and see how much, if at all, ZFS is correcting errors caused by space radiation or hardware failure. So that's all I had.
Hello, my name is Satish. A couple of questions, actually. What's the altitude the mission's going to be flying in? And the second question is, if you're doing TMR, do you see the value of ZFS on top of TMR?
You mean triple
modular redundancy?
Modular redundancy. So for the altitude question, I think 400 and something kilometers. I don't know the exact answer. For triple modular redundancy, we're not actually doing that for this mission. I was just mentioning it as one possible strategy. And in this case, we only have one drive for each Linux system, so we're not doing RAID either. We're just making copies of the data within that drive.
I have a question about ZFS. One of the issues that I've always found with ZFS is it takes a lot of memory. One of the reason it's not the default file system is because it does chew up quite a bit of your RAM. Is that something that's a factor in your system?
No, I haven't really run into that issue. I know that there are some features of ZFS that especially use a lot of memory, like block deduplication and compression. So we only turned on those features on certain parts of the file system and not all of it. But in general, haven't noticed much of an issue with memory usage.
Yeah, a follow-on question along those lines. There are questions about benchmarking, read-write operations, whether you have tried different hardware, whether you have done some benchmarking.
We have checked, what read and write speeds we're getting, but our main consideration for the hardware was, radiation tolerance, so it wasn't as much about performance. Hopefully that answers.
Line, it says, how does ZFS handle corruption of the checksum?
Corruption of the checksum. So in cases where you have multiple, well, I guess if your checksum is corrupt, then it's not going to match the data. So then ZFS would go look for another copy of the data or another copy of that file system metadata. Unfortunately, in the case of the metadata, there's always another copy available.
All right, there are more questions coming in. One is whether it does the handle wear leveling.
Wear leveling? I think so, but I'm not sure.
No more
Other questions?
other questions? There are a few online, but we are running out of time. So
Okay.
please follow up with,
Okay.
on Slack channel. Thank you so much.